record. Alright. Any in particular that's jumping out at you on chapter 3? Any in particular? Number 1. Okay, so we're at chapter 3, problems. Number 1, page 93. Alright, so we got a squirrel that has a coordinates of, so we got Shirley Squirrely here, pointed ears, and a body, and little legs, and a bushy tail. Alright, now, looks like a cat, whatever. Alright. And it has coordinates at time 0 of what? 5.3 meters. And, no, excuse me. 1.1 and 3.4. And then at time 3 seconds, the coordinates are 5.3 and negative 0.5 meters. Alright, so if you were to graph it, what would it look like? At time 0, alright, 1.1 and 3.4. So probably somewhere what, like right here? And then at time is equal to 3 seconds, where would he be? He's at 5.3 and negative 5, so he's somewhere like over there, like that. Okay? Alright. So he changed his direction, doesn't he? He was going northeast, now he's going east-southeast. Actually north-northeast. Now he's going east-southeast, okay? Alright, so for this time interval, find the components of the average velocity. Alright, so let's look at that first. So part A, we want to know velocity average of I and J, right? Or X and Y. Okay? We want to know the components. And the magnitude direction of the average velocity. Okay. Alright, so how do we define average velocity? Oops. Velocity average, by definition, 9th grade definition, is what? Delta R over delta T. Now remember, why am I using delta R? Because now we're talking about motion in 2 directions. 2-dimensional motion. Okay? So instead of saying delta X, we say delta R, and that means the difference in both X and Y. Initial and final. Okay? Right? Okay, so let's look at it then. Let's do the velocity average in the X or the I direction. And so we say what? 5.3 minus 1.1. And the time interval is what? 3 seconds? Okay? Of course, that's meters. And what do we get? 1.4 meters per second. Now look, we can write it this way. Caret cap, I caret cap, okay? Or X, okay? And then the velocity average in the Y is what? Negative 0.5 minus 3.4 divided by 3 seconds. And what do we get? Should get a negative. Negative 1.3. And we would put our parentheses around that and say J. Okay. All right. So there's the first part, the components. So the components are what? Velocity average, we would say what? 1.4 meters per second I minus 1.3 meters per second J. All right? There's your components. Okay, now the B part says do what? B part says how far, excuse me. The magnitude and direction of the average velocity. Okay, now we have components, but how do we find the magnitude? All right, this is part B, number 1. So how do we find the velocity magnitude? You got an I and you got a J. Remember, now let's graph that real quick. What would that look like? Okay, we got a positive 1.4 and a negative what? 1.3. So my line's going to be what? Something like that right there. Right? This is Y and that's X. Right? It's going to look something like that, isn't it? Because look, where do those coordinates put me? They put me right there. Right? I know I didn't draw a scale, but again, just notice that the direction in the X is almost the same as the direction in the Y. The Y is just a tad greater, isn't it? Oh, no, a tad less. Excuse me, a tad less. 1/10 less. Okay, so, but now wait a minute. I want to know the magnitude. I don't want to know the components. So what have I got to do now? Remember, y'all, anytime you see the word magnitude, most of the time you got to do the square root of the squares. And what do you get? 1.91. Okay, 1.91. So anytime it's asking for the magnitude and you have components, then you have to take the square root of the squares of the components. Remember Pythagorean theorem. Okay? Does that make sense? So remember, terminology, learning terminology. When you hear the word magnitude or speed, what is the speed? And you had components, you had X and Y components, you've got to take square root of the squares on those, okay? All right? When you have components, I and J, X and Y, okay? All right, now how do we find the angle? Well, that's easy. We do arctangent, don't we? And where does that come from? Well, it just comes from tangent theta. And so we got what? -1. Yes, that negative has got to go there, over 1.4. And what do we get? We get -42.9, don't we? Now, okay, is that the answer I want to see? No. Okay, because that really don't tell me anything. Okay? It's not a proper way to measure angles. All right? So we got to orient it from counterclockwise back around that way. Okay? And so what quadrant is that in? It's in the 4th, and it's negative. So what do? I say 360 minus 42.9 is equal to 317.1, right? And that's what we want to see. And does that make physical sense? Well, sure it does. Because look at your X and Y components. Look how small they are, and look, all right, this is 270. Okay, so 30 more is 300. So yeah, that sounds like 317. Looks like 317-ish. Okay? Okay, and that's what we want to see on the exam. And always circle your final answers. Make sure the proper units are there. Okay, always. All right. Okay, we good? You need to mark that question because that could be a question on the exam. So go ahead and put a mark on it. I'm just going to cover these while we go, and then go back and pick up the rest of them. I'm going to be real nice and I'm going to narrow all these questions down to just a few, okay? In other words, instead of having about 40, you're going to have about 12 or 15 to look at. Okay? All right. And we're going to do that here in a little bit. Okay, any others that's jumping out at us screaming and saying, help, help, help? Number what? 3? Okay. Number 3. Go ahead and mark that one too. All right, so we've got a web page designer creates an animation in which a dot on a computer screen has position of R is equal to. All right, so we draw our axis. We got a dot on a computer screen. I'm just going to say it's right there. And it's R is equal to 4 centimeters plus 2.5 centimeters per second squared. T squared I plus 5 centimeters per second T J. Put my carrot cap on it. Okay? That's a T. Okay, not a plus, T. Okay? All right, so that is the position of that dot. All right? Find the magnitude and direction of the dot's average velocity. Average velocity for times T is equal to 0 and T is equal to 2 seconds. So we're looking at velocity average at time equal to 0 seconds and time is equal to 2 seconds, right? All right, so that's A, right? Yeah. Okay? All right. Okay. All right, so what do we do? Notice that's R. And R is displacement, correct? Sorry about that. Put it on vibe. Okay? R is displacement. In other words, it's X and Y. Okay? But we got to have velocity. We got to have average. Now notice it said average velocity. It did not say instantaneous. That's part B. Okay? So how do we find average velocity? Okay. Velocity average is what? Delta R over delta T, isn't it? Remember I told you when we got into chapter 3 that the equations did not change. The only thing you're going to change is putting that R in there because now we're talking about I and J, okay? Right? Okay. All right. So we've already got R. So now all I got to do is just plug in my times, right? Okay, well let's look at it at time is equal to 0 seconds. Plug it in. We got R is equal to 4 centimeters plus 2.5 centimeters per second squared times what? Now watch. 0 seconds squared I plus 5 centimeters per second times 0 seconds J. Wow, that becomes really easy, doesn't it? Look, those are gone, those are gone. All you're left with is what? R is equal to 4 centimeters, isn't it? Now that's at time 0. Time equals 0. What about R at time equal 2 seconds? Well, plug it in. So we got 4 centimeters plus 2.5 centimeters per second squared times 2 seconds squared. Close the brackets. Oops, that's a brackets. I, carrot cap, plus 5 centimeters per second times 2 seconds J. Then what do we get? We get 14 centimeters I, right? We get 14 centimeters I plus what? 10 centimeters J? Yeah? Okay. All right. All right. Then listen very closely. Notice what it says. It says find the magnitude, all right, direction of the dot's average velocity. Average velocity. All right, now we're still not done. Okay, so what do we got to do? Well, we got to do velocity average, don't we? Velocity average is what? Delta R over delta T. All right. So what do? We do it for each part, don't we? We've got at time 0, right? It is what? 14 minus what? 14 minus 4? Or excuse me, I'm sorry. Just to find the average velocity. We do what? Final minus initial, don't we? Well, we got 14 centimeters minus 4 centimeters over 2 seconds. And this is going to be the I component, right? And what do we get? 5 centimeters per second, is that right? And that's I. And then same thing for J. We got what? 10 centimeters minus 0 centimeters over 2 seconds. And we get what? 5 centimeters per second J, right? So technically we could write the average in component form. Now this is component form. 5 centimeters per second I plus 5 centimeters per second. Oh, shoot. Please tell me that didn't delete. Oh, thank God. There it is. Centimeters per second J. All right, but now we're still not done. It says what is the magnitude? What is the magnitude? All right, well, we've got 5I and 5J, don't we? Remember what it says? Remember what we do when it says magnitude? All right, so the velocity magnitude is equal to the square root of the squares, isn't it? 5 squared plus 5 squared is equal to what? 7.1? Is that right? Is that right? All right, but now how do we find the direction? Arctan, right? Arctangent. So we got arctan is equal to what? 5 over 5. And that comes out to be 45 degrees, doesn't it? Okay. All right. So now that's part A, isn't it? All right. Okay, can I move on? All right, now what about part B? Then it says find the magnitude and direction of the instantaneous velocity at time 0 and at time 1 second. Okay? Well, now notice we've got the R. Now, to find instantaneous velocity, what do I have to do to that R? R is not velocity, is it? And it's asking for instantaneous, so I do what with the R equation to get it into velocity? Remember? Take the derivative. And so then the velocity is equal to, well, what happens to the 4? It's gone, isn't it? And then it becomes 2 times 2.5. Can I do this right here? Can I just go ahead and say 5? Well, no, I'm not going to do that. No, I'm not going to leave a step out. All right, so 2 times what? 2.5 centimeters per second squared times the what? Times the time and that's I, plus, and then we take the derivative on the other side, and it becomes what? Just 5 centimeters per second J, is that right? Because the T's gone. Take the derivative of T, it's 1, right? Okay. Okay. Now we just do what? We plug and chug, don't we? Okay, y'all, what is the initial velocity going to be at 5? Oh, excuse me, at time 0. At time 0, what's the velocity going to be? What happens to this term right here when you plug in a 0? It's gone. So all we're left with then is what? 5 centimeters per second J, correct? What about at time 1 second? Okay, well we got 5 centimeters per second I, right? Because look, plug in 1. 1 times all that is what? 5. Plus 5 centimeters per second J, right? Okay. Now we got to do what? Find the magnitude and the direction. All right, let me make sure I read it again here. Do what now? Oh, do we have to do it for time 2 also? Why did I do 1 second? Oh, I'm sorry. Thank you. All right, so at 2 seconds, what is it? All right, we got, what, 10? Is that right? Is it 10 meters per second? Yeah. Centimeters per second, I'm sorry. J. Now look, you see what I'm doing, don't you? Take the 2 and plug it in right there. Okay. Plus what? Oh, dang it, that's I. That's an I, not a J. That's the J. My bad. Okay. Okay. Okay, now we got to find the what. Okay, what is the, and we have to do each one individually, don't we? All right, what is the velocity instant, what is the magnitude right here? We've got 0 squared plus what? 5 squared, and that equals what? 5 centimeters per second? Is that correct? All right, what is it for this time? Velocity average. All right, we got what? 5 squared plus 5 squared, and what do we come up with? I'm not doing something wrong, am I? No. Am I? What's 5 plus, isn't that, we just did that, didn't we? It's 7.1, isn't that right? 7.1. Dadgummit, there it goes again. Okay. And then what about right here? Velocity magnitude is equal to, all right, let's do, we got 10 squared, right, plus 5 squared. And what do we come up with? Isn't it 11.2? Yeah, 11.2 meters per second. Centimeters per second, excuse me. Is that correct? Okay, now what are the directions on each one of these? Does it ask for direction too? Boy, this one's long, isn't it? Yes, it does. All right, so what is it? All right, well, let's do it for each one. All right, what is the theta for this one? All right, we've got what? Y was what? We got 5 over 0, right? Is that right? Yeah. 5 over 0, and that's what? Undetermined? 90 degrees, yeah. I mean, we can't do it. Well, we can, but it's 90 degrees. We know it's 90 degrees. How do we know it's 90 degrees? Well, look at your value. You have no x value. It's 0, and y is all you have. So that means it's straight up. So it's 90 degrees. Okay, so that one is 90 degrees. All right, what about the next one? Theta is equal to what? Well, we've got arctangent of what? 5 over 5. And what does that come to? 45? Is that right? So that's 45 degrees, isn't it? So this next one then looks like this. Okay? All right. And then the last one, arctan, is what? 5 over 10? Yeah. And what does that come to? 26.6 degrees? And so this one's going to look, going to look something like that. It's a little bit low, but anyway. Everybody good? Okay. All right, so what does it say in the last part? Sketch a dot's trajectory and show the velocities calculated in part B. Okay. All right, this is, well, it's not tricky. You just got to be careful what we do here. All right, so if we say 2, 4, 6, 8, 10, 12, okay. All right. Ah, dang it. Why did I do that? My bad. What's going on? The computer's really acting crazy. That don't want to erase now. Look at that. Okay. All right. It's going to look something like this right here. Velocity versus time. Except not quite as flat over there. It'll be gradually. Once it gets past the hump, it's gradually going to be going up. And I'm not going to ask you to draw stuff on the test. Okay? All right. Any others? Did y'all do the fireman problem? Okay. Did you mark number 3? Number 1, number 3 you need to mark. Number 7, number 9 you need to mark. Number 20 you need to mark. And number 27 you need to mark. All right. Let me say that again. 1, 3, 7 and 9, 20 and 27. And we'll do chapter 2 here in a minute. Okay. I think we've already done number 9. What about number 20? Number 7? Oh, okay. Number 7. All right. The coordinates of a bird flying in the XY plane coordinates of a bird flying in the XY plane. All right, so let's draw it. All right, so we got a bird here. All right, wings there. Bird flying in the XY plane are given by x with respect to time is equal to alpha t, and y with respect to time is equal to 3 meters minus beta t squared. Okay, that's minus there. Okay, all right, and alpha is equal to 2.4 meters per second, and beta is equal to 1.2 meters per second squared. Sketch the path of the bird at time t and at time 0. Excuse me, time 0 and time 2. Okay? So we want to know the path. So A, all right, so at time 0, all right, at time 0, what do we know about the bird? It only has what? If I plug a 0 in right there, what do I get for x? 0. If I plug a 0 in right there, what do I get for y? 3. Huh? Look now, that's 3 meters minus bt squared. There's no t on that 3, right? So does it stay? Huh? If I plug a 0 in right there, that term is gone, but I'm left with 3 meters, right? Right? Isn't that the function? Is there a t on that 3 meters? No. Can I plug a 0 in there? No. Okay? Because it's 3 meters minus beta t squared. So if I were to draw it, then the dot would be what? Right here, and I would have an arrow going straight up, right? 90 degrees, right? Okay. What about at time 2 seconds? Okay. At time equals 2 seconds, what would it look like? Okay, plug in a 2. 2 times 2.4 is what? 4.8 in the x. What is it here? Well, 2 squared is 4 times 1.2 is what? So 2 squared, or 4 times 1.2, that's a negative what? 4.8? So 3 minus 4.8 is a negative 1.8, is that right? All right, let's just plug it in. All right, so we got x with respect to t equals 0. All right, so we got alpha times 0, so that's equal to 0 meters. And then y equal to 0, we got what? 3m minus what? 1.2 meters per second squared times 0, and that's 3m meters. And then x t equal 2, what do we got? We got 2.4 meters per second times 2, and that's what? 4.8. And then y t equal to 2 seconds is equal to 3 minus what? 1.2 meters per second squared times 2 seconds, and that comes to a negative 1.8, right? All right, now what will that look like on a graph? Whoa, 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 whoa. Where? Oh, over here. Yeah, thank you. Thank you. Yeah, squared right there, too. All right, so what does that look like on a graph? It's going to look something like this right here. Something like that. Notice that y is negative and it's a small amount, but x is 3. It's about twice y, right? Almost twice. Is that what it would look like on a graph? Okay, I hope. Calculate the velocity and acceleration vectors of the bird as a function of time. Okay. Okay, so what would the velocity be? All right, well, we've got y with respect to t and x with respect to t. So how do I calculate velocity? I got to do what? Do what to those functions? Take the derivative, right? And so what are we left with? Alpha and Vy is what? 3 meters minus what? 2 beta? 2 beta what? T? Right? Is that correct? I had to take the derivative, y'all. Don't forget. All right, so V in the X at time 0 is going to be what? Well, what was alpha? 2.4? Yeah. So it's 2.4 meters per second, isn't it? What is Vy time equals 0? Well, when you plug a 0 in there, you got 3 meters minus 2 times 0. So it's 3... No, wait a minute. Is that 3 meters? Or 3 meters per second? No, it's 3 meters, isn't it? Oh, shoot. Why didn't y'all call me on this? My bad. That term's gone. Minus BT. Minus BT. There we go. Sorry about that. Now, so what is it in the Y direction? Oh, crap. It's been a long week. All right, so you've got 1.2 meters per second squared times 0 seconds, and that's equal to 0 meters per second. Right? Does everybody see what I'm doing? You see I had to take the derivative. I cannot calculate the vectors. What do you mean? What does that mean? That means you got to calculate the components. And I can't do it without taking the derivative. Okay? It didn't ask for average velocity. Didn't ask for average velocity. Okay? All right. Now, what is it at time 2 seconds? So we got, well, look, it doesn't change here, does it? And that's X. And Vy at 2 seconds is what? 1.2 meters per second squared times 2 seconds. And what do we get? 2.4? Oops, negative 2.4. Right? Is that correct? Did I do that right? I better have. Yeah. Yeah, velocity is 2.4. Negative, yeah. All right, now, what is the acceleration going to be at these times? All right, y'all, take the derivative of those equations. What do you come to? 0 meters per second squared, don't you? Acceleration in the Y is what? Negative beta? Right? Take the derivative of Vy is equal to, do dB dt. And what do you come up with? Negative dB. Right? Negative beta, excuse me. All right, so the acceleration in the Y is going to be what? 1.2 meters per second squared. Is that right? Oh, shoot, it's 2 beta. Dang it, dang it, dang it, dang it, dang it. It's 2 beta. That's not right. That's wrong. Y'all got to watch me, I told you. It should be 2 times that 4.8. I'm sorry. There we go. I left the 2 off right here. That's supposed to be negative 2 beta. And then it's what? Negative 2 beta. I'm sorry. Now it's looking better. All right, so it becomes what? What is 2 times what? 2.4 meters per second squared. There we go. I knew something didn't look right. Okay. All right, everybody see what I'm doing? You just got to take that derivative and plug the times in. All right. Then what does it ask? Part C. Sketch the dots trajectory. Fine. Whoa. And the direction. I didn't find the direction. Okay, what's the direction of the velocity? Okay. I'm looking at the wrong problem. All right, calculate the velocity and acceleration vectors. Okay, the function. Calculate the magnitude and direction of the bird's velocity and acceleration at 2 seconds. At 2 seconds. At 2 seconds. So that's 7C. All right, did we fulfill part B? Calculate the velocity and acceleration vector. Yes. All right, so what is it? At x, it's 2.4. At y, it's 0. And then acceleration, at x, it's 0. And at y, it's 2.4. Notice how they flip. Now, part C. Calculate the magnitude and direction of the bird's velocity and acceleration at time 2 seconds. All right, so let's take our 2 seconds. Okay. And so what is the magnitude of the velocity at 2 seconds? The velocity magnitude at 2 seconds is the square root of what? 2.4 plus what? Negative 4.8. And what do you get? 5.37. And what's the angle? Negative 4.8 over what? 2.4, and that comes out to be what? Negative 63.4 plus 360. And then that comes out to be what? 296.6. All right, now what about the acceleration? All right, acceleration magnitude, square root of 0 squared plus what? And that's a negative, dadgummit, negative 2.4. And that's all on the radical squared. And what does it come out to be? Well, negative, it comes out to be what? 2.4 meters per second squared. What's the angle? Theta is equal to arctan. And we got what? 2.4, and that's negative over 0. Uh-oh. So in other words, it's straight down, isn't it? 270 degrees. All right, so notice that the acceleration is straight down, and the velocity is at 296.6, so it's kind of moving at an angle to the acceleration. Right? Sketch the velocity and acceleration vectors at time 2 seconds. All right, so let's look at that now. Part D. All right, so what is the bird going to be looking like? Okay. Okay, so at time 2 seconds, okay, we're at what? What was our velocity? 2.4 and negative 4.8. So at time 2 seconds, it was 2.4. Let's just say this is 2 seconds. It was at 2.4x and 4.8y. Right there. Right? This is velocity versus time. Is that correct? Now, where did we begin? Well, at 0 seconds, what was it? It was 2.4x. So the bird is doing what? Going that way, right? Now this is at 2 seconds, okay? What about the acceleration at 2 seconds? All right, it's 0x, but it's what? Negative 2.4y? Yeah. All right, watch. Acceleration versus time. 0x, 2.4y. So the bird's speed is what? Increasing or decreasing? Notice they're both generally going in the same direction. It's increasing and it's turning which way? If your velocity vector is this way at an angle and your acceleration is this way, all right, let's think about it. Velocity, but you're accelerating that way. It's turning to the right. So you kind of gotta look down the x-axis. It's increasing and turning to the right. Look at it. Velocity vector is going that way. Acceleration is going that way. So that means it's going to do what? It's pulling the bird to the right. Does that make sense? See, we're looking at two separate parts, but you got to think about physically as that bird's flying. If he's flying this way, but the acceleration vector is this way, it's pulling him to the right. Okay. Whew, that was a long one, wasn't it? So he is increasing. Now, I'm not going to get into all that on exam. Y'all, I can't ask you 4 or 5 parts on a question on exam. I mean, good Lord, we'll be here all day. 1 to 2 parts and that's it. No, you're not going to draw any graphs. No, we're not drawing any graphs. So increasing to the right. Yeah. Now, if his velocity vector had been the other way, had been going up, okay, then he would have been decreasing speed, wouldn't he? And going to the left. Yeah. Okay, because see, if the acceleration was this way and the velocity's that way, well, they're opposite each other. See? If acceleration was going positive instead of negative, and the velocity's going this way, then he's slowing down and turning to the left. Okay? Think about braking a car. Which way does acceleration have to be for a car to stop? It has to be in the opposite direction of the velocity, right? Okay, think about it that way. Okay? All right.